So Siddharth came to us with a degree in engineering and has been combining both those skills and the physics skills that he's learned here as part of this DMREF Networks project, which I just want to say a little bit about because I think it's interesting. DMREF aims to fund projects where making samples and designing new materials is challenging, and so you want to do it in concert with both theory and simulation, and you sort of use the experiments to make sure you know what's going on in the real world. But a lot of the heavy lifting is often done during the simulations and the theory, and then it comes back to the experiment again to check things again. And so you're going to hear about a lot of other people who are involved in this project, and that's because a lot of other people are involved in this project by design. There's 5 PIs, right, and the stuff is circulating among the whole group. And so this is a little bit different. This is an incredibly collaborative program by design. And so Siddharth is going to defend the part that's absolutely his, and he is the expert on. All right, take it away.
So, good morning, everyone. I would be presenting the study of acoustic properties on hyperuniform-based metamaterials that I have been working on under Dr. Daniels. You will see there are different systems on the slide here. There are prime numbers, that is a large-scale structure of the universe, like how matter is distributed. There are Penrose styling, cells in chicken eyes. There is like sphere packing, which is often used to model granular systems. And all the systems might look different, but they have a similar kind of arrangement in which, by which I mean that they are disordered, but at longer length scales they show uniform nature. And by that I mean fluctuations in density at large length scales vanish, and that property is called as hyperuniformity. And many of these systems in nature happen to be hyperuniform for various reasons, for optimizing physical properties. For example, if you take chicken eye cells distribution here, then it happens that there are 5 different types of photo detecting cells in chicken eyes, and they are of different size, and you cannot tile a space with a regular shape with 5 different shaped sized circles. And so by that reason it has to be a random kind of arrangement. But it would be better for chicken if it had as dense of a packing of cells as possible. So, as it turns out, nature selected a distribution which results in a hyperuniform but not ordered distribution. And various other systems have been found in nature for different reasons. Some of them we know the reason for, some of them we don't yet. And so the question is, can we use this kind of property to control physical properties of materials that we design in real life? And that is what this whole project is about to find out. Computational and theoretical studies have already shown that desirable properties like band gaps, spatial distribution of vibrational modes, and transport properties exist in hyperuniformity-based metamaterials. This diagram here shows concentration of vibrations, and colors are representing in and out of plane vibrations, and you can see plane waves, you can see dispersed modes of vibrations. This here shows a band gap along the frequency in some intermediate region, and these metamaterials also pose a manufacturing challenge, since some of these, especially in 3D, some of these designs can have excessive overhanging beams which are hard to be manufactured, and even it's challenging in additive manufacturing that we use. And there have been recent developments also from Camel at Centennial here by the team of Dr. Rock, on developing methodologies for being able to manufacture some of these hyperuniform metamaterials. I stick with 2D metamaterials in this study primarily because they are easier to manufacture, and also the methodology for measurement of acoustic properties were easy to develop in that case, and it's not known yet how we could measure the acoustic properties and spatial distribution of vibrations for a three-dimensional metamaterial. And those are like some of the properties that have been predicted in theory and computation that I just talked about. My goal would be to find desirable phononic properties, acoustic properties of these metamaterials. I would specifically be looking for band gaps, different spatial distribution of vibrations, and also if we could contain vibrations in a concentrated place, or if we could have a variety of dispersed vibrational modes. And I would also be looking for if there are any parameters throughout this design process which would turn out to be a tuning parameter, which we could use to control, let's say, the location of band gap, or control what exact location the concentration of spatial vibrational modes occur at. And so, to start with, I would like to quantify hyperuniformity. There are multiple ways of quantifying hyperuniformity. One of them is number variance. So imagine tossing a disk of some radius r on a 2D plane of point distribution, and count the number of points included inside the circle. So across multiple different disks, we would get a number variance of number of points contained inside the disk, and a material is said to be hyperuniform if this number variance grows slower than the volume of the observance window we have as the radius grows, and that is shown by this number variance. And in two-dimensional, D would just be 2 here, but this could be applied in general to D-dimensional spaces and points distributed in D-dimensional space, where volume of the observance window would be proportional to R to the D. Another quantity which is often used to quantify hyperuniformity of a material is a structure factor, and this is analogous to the previous quantity where this is in Fourier domain, and K here it measures the wave number, and smaller the wave number, larger is the length scale across which we are doing the similar kind of process as previous one, measuring the density fluctuation. And a material is said to be hyperuniform if structure factor goes to 0 as wave number goes to 0. But given that this is about separation of density fluctuation at longer length scales, we could have distributions that go to 0 at longer length scales at slower rates or at faster rates, and that allows us to have different flavors of hyperuniformity depending on how quickly the density fluctuations are suppressed. And 3 different classes are often categorized in literature. The class 1 here is the most hyperuniform. Class 1 also includes some of the ordered crystalline arrangement of points, and these are like trivially hyperuniform because they are ordered everywhere and they would have similar density everywhere in the space, and so fluctuations in density are identically 0. But class 1 also includes some of the distributions that are called stealthy hyperuniform, which are not ordered, but their density fluctuation still goes to 0 identically at finite length scales instead of infinite length scales. So to design metamaterials, we first need to, let me just get some water. we need to start with a hyperuniform point distribution, and this is done by our collaborator James Raj from UCLA. And there are various ways of getting a point distribution, and once we get a point distribution, then we connect them, and there are various protocols of how we decide to connect the points to form a network. That is the skeleton of metamaterial. And some of these parameters could ultimately turn out to be tuning parameters which do control properties of metamaterials, and sometimes they may not, and that's what I aim to find out. The starting point distribution could be random, it could be ordered, or it could be a known hyperuniform distribution. And there are various protocols that exist that I will explain in upcoming slides, and those include Voronoi tessellation, Delaunay triangulation, or Gabriel graph. There is a way of generating point cloud which is called uniform randomized lattice, and in that we start with uniform ordered distribution of points, and since our ordered distribution of points is known to be hyperuniform, it is also known that uncorrelated uniform perturbation of these points also turn out to be hyperuniform, and we could control the amount of disorder by controlling the parameter A, which defines the window here, the size of the window. Size of the window that determines the strength of perturbation, and let's say the interparticle spacing between the original point cloud is D, then A is a fraction of that spacing, so it is quantified in relation to the interpoint spacing of the original point cloud. And once we have such a point cloud, we could have multiple different protocols of connecting them. So in Gabriel graph, we consider a pair of points at a time, and we decide whether to connect or not that point depending on whether the line segment connecting the 2 points forming diameter of a circle includes a third point to the interior of the circle. So if there is a third point to the interior of the circle formed, that is defined by the diameter of connecting 2 points, then we do not connect those 2 points. However, if there is no other point to the interior of the circle, then we do connect those 2 points. And a sample network generated by using such a protocol is shown in this graph on the right. The URLs are known to be all the URLs of all the different perturbation strengths are known to belong to class 1 hyperuniformity, and the parameter A gives us independent control over the amount of disorder we have in the system, and the specific different strengths of disorder I use are 0, 0.2, 0.4, 0.6 and 0.8 and 1. These are again fractions of the original ordered interpoint spacing between the original point cloud that I start with before perturbation, and those are the characteristics I just described. I would also show some of the preliminary data for a different kind of metamaterial generated from a point cloud as dictated by something called Lloyd's algorithm, and then I do Delaunay triangulation, which is a rule of how we connect the points that we get out of Lloyd's algorithm. So in Lloyd's algorithm, we start with defining Voronoi cells, and starting point distribution for a Lloyd's algorithm could be random or could be ordered. It could be uniform or not uniform. And so if we have any kind of point distribution, the way we define Voronoi cell is, given a point, we consider all the locations in the space, and we assign that point a cell region for all the which is collection of all the locations which are closest to that point than any other point. So for example, if I look at this point here, then all the region up till this border is closest to that point, and all the region after that point is closest to this point, and so this region belongs to this cell generating point, and the other region belongs to the other cell generating point, and that tessellates the whole space, and the boundary lines we get between the individual cells are the Voronoi, forms the Voronoi network. Once we have Voronoi cells, we find centroid of all the cells, and we consider new centroids that we found for each cell as cell generating point for a next iteration of the algorithm, where we again find Voronoi cells for the centroids of the older Voronoi cells. And I've looked at centroids of some of the cells here, and these would again in turn be used in the next iteration of Lloyd's algorithm to define Voronoi cells. And this algorithm is, as I said, is known to iteratively increase the degree of hyperuniformity. If we start with an ordered point distribution, then this algorithm wouldn't do anything to it, because Voronoi cells and cell generating point of Voronoi cells and the centroids of those cells overlap. They're in the same location. So we generally start with a disordered hyperuniform distribution. So once we obtain varying degree of hyperuniformity out of varying number of iterations of this algorithm, I use the metamaterials that are connected using Delaunay triangulation. And Delaunay triangulation is dual to the Voronoi Delaunay triangulation, which is shown in the black color here, and the background, which is red, is the Voronoi tessellation. Here are two examples of two different Delaunay triangulations whose original point distribution has been taken through. The first one has been taken through one iteration of Lloyd's algorithm, and second one has been taken through 30 iterations of Lloyd's algorithm. The additive manufacturing methods, we use laser powder bed sintering, and the manufacturing was done by Dr. Rock and his team, including Molly Lee and Catherine Moody at CAML, which is Center of Additive Manufacturing and Logistics at the Centennial campus here. And we use nylon 12, which is a proprietary material given by Formlabs, and some of the properties of the material are listed here, which I would come back to later while deciding measurement range and how I would measure the acoustic properties of the material, describing my experimental setup. So once again, what am I looking at in this experiment? I'm looking at the frequency content, and I'm looking at frequency content of the vibrations in the metamaterial, because that helps me look at the band gap regions, and also I'm looking at spatial distribution of vibrations. And what kind of experimental setup would I need to look for these features? I would first of all need to drive my system, and I drive my system with white noise, which is sum of all the frequencies, and if there is any frequency that cannot pass through the medium, which cannot pass through the material, then that region would form a band gap like feature. If there are some frequencies for which it stays concentrated in the metamaterial, then that would allow for concentration of vibrations in the metamaterials, and if they show low loss of vibrations, then these could be used to store energies in vibrational forms. So my experimental setup here is I use a Siglent wave generator, and I drive the piezoelectric with white noise of 1.2 volt standard deviation and mean of 3.949 volt. Mean is not at 0 to account for asymmetric amplification by the amplifier. Amplifier gives a 15x gain. However, on the negative side, it cuts off beyond a certain region. Any of the voltage amplitudes that go beyond a certain value, and I found that the 3.949 gives most amplification without asymmetrically cutting off my signal. The piezo has resonance of 115 kilohertz, and the range of amplification of my amplifier is from 100 hertz to 100 kilohertz, and that way I avoid the resonance peak of the piezo, and which prevents me from capturing something that is a feature of piezo instead of the feature of metamaterial while I'm testing the metamaterials. My experimental setup also includes a laser Doppler vibrometer, and it works on the principle of Doppler shift. Doppler shift measures the frequency change if an object is moving relative to the laser Doppler vibrometer, and that gives me V of t data for a continuous scanning. V of t data could be Fourier transformed, and in Fourier domain I would get V tilde of f data as a function of frequency, and that allows me to examine the frequency content of the vibrations in the metamaterial. The metamaterial I used, which are made from nylon 12, has Poisson ratio of 0.4. So any kind of vibrational sound waves that exist in plane get converted, the compressions and expansions get converted to respective compression and expansions out of plane, and that helps me measure vibrations present in the metamaterial. And that is, as I said, how I get V of t data using Doppler shift from laser Doppler vibrometer.
Sorry, can I ask like a quick clarifying question?
Yeah.
You're measuring it at just one spot, is that right?
I decide spots at which I will measure,
Okay.
and it spends some time at each point gaining the data, and it moves on to a new point, gains data,
Got it.
and moves on to the next other question. There are many quantities in frequency domain which we could use to study the frequency content of a metamaterial. I use something called power spectral density, and more familiar quantity is if you put power spectral density of velocity on logarithm scale, you get something which you're more familiar would be, and that is decibels. I just grabbed 2 clips from internet to explain how I distinguish characteristics of 2 different things, and these audio clips were obtained from Citizen DJ website. One of them just happens to be called Bad Guys. I did not choose it for the name, and that's what Bad Guys sound. Oops, it's mixed with my voice. And the second one is Interview in a Pub. A bit serious, but we can distinguish what an interview in a pub sounds like from what Bad Guys sounds like. There are many distinguishing features in the curves here, but if we look at the end regions, which are like more prominent distinguishing features, the clip Interview in a Pub lacks the higher frequencies and the lower frequencies, whereas Bad Guys don't. And that's how we can distinguish one from another. A sample measurement of what laser Doppler vibrometer gives out is I define a point, and this is just a sample measurement where I put a single point on a spot, and these tests were run by one of my collaborators, Veronica, in the lab, where she puts one single point to scan, and data comes out something like this, and this is power spectral density, and I could compare this plot with plot of some other scan point, and that would give me that would allow me to compare different characteristics of the curve. So for range of measurement, what range should I be measuring my frequencies present in metamaterials? For that, I decided to do resonance calculations for individual beams in the metamaterial, as well as on the scale of the bulk of the metamaterial. For individual beams, I found that a resonance frequency would occur around 63 kilohertz, and for the lattice scale, I find that I would see something like a plane wave around 4.3 kilohertz. And to include these both in my measurements and have I start measuring from 500 hertz to 100 kilohertz, and that way I have the first of the resonance of individual beams centered in this range. And because after perturbation the beam lengths are not there isn't a single beam length for a metamaterial like there is in an ordered point cloud. The beam lengths would be distributed around the length of the original point cloud, and so I would expect most beams to have their resonance distributed around 63 kilohertz, even though not exactly at 63 kilohertz. So any experiment to be able to conclude that what I find, to be able to attribute that the outcome I see in vibrational modes is due to something that I control, I need to be able to isolate variables, and any experiment has multiple different variables that could affect the measurement. And here I found that few things that affected my measurement that I did not want to find the characteristics of were using different piezos gave me different power spectral density curves in lattices. Changing tension for some of the lattices gave me different power spectral density curves. I paste my piezoelectric to the metamaterial for driving, and I found that different curing times and different glowing sessions affected my power spectral density curves for the metamaterial. And so I tried 5 different tensions, and for least perturbed or unperturbed point cloud, a network generated from that point cloud, I saw that the Bragg peak around 63 kilohertz gets non-monotonically attenuated or amplified depending on tension under which I held my metamaterials. And as you can see, for lowest of the tensions, which is 0.1056 newtons, my Bragg peak is highest, whereas for second lowest, it has completely vanished, but then it reappears for third, and so on and so forth. So it has a very non-monotonic behavior under tension. And some of the intermediate tensions for which the Bragg peak completely vanishes is below 2 PST. Also found that perturbation strength of 0.8 has a tension dependence, and it has a very non-linear tension dependence, non-monotonic tension dependence as the previous one as well, and the dependence varies across different peak features for this metamaterial. For first of the peaks, around 3 kilohertz, for 3 of the tensions I tried for this metamaterial, the peaks mostly agree. Whereas for second peak around 4 kilohertz, the peaks don't agree under different tensions that I've tried. Under at 5 kilohertz mark, again the peaks don't agree, and there is a peak which isn't present at all in 2 of the tensions, but is only present in the 2 Newton tension that I've tried this metamaterial under. So to control the tension and achieve reproducibility across measurements, I found that using a spring of 35.2 newtons per meter gave me good enough control over tension by controlling the extensions in the springs. And if I vary the spring extension over a few millimeters, 3 millimeters, 0 millimeters to 5 millimeters, I find that I get roughly the same curve. So my control over tension now is better than the sensitivity of the metamaterials to the tension. Next, I also found that gluing time, the curing time of the glues, affects the measurements of the power spectral density I get out. I tried 3 different curing times: 20 minutes, 2 hours, and 20 hours. And I found that especially the higher frequencies, around 5 kilohertz and 9 kilohertz, are affected. The peak at 9 kilohertz only appears for curing time of 20 hours, whereas it is not present in any of the other curing times. And this is presumably due to change of viscosity properties of the glue over time. Even the glue appears to be visibly solidified, and that changes its ability to being able to transmit some of the frequencies. But then I also found that curing time of more than 20 hours, for example, here I compare 20 hours and 96 hours. There isn't an appreciable difference in power spectral density curves I get for the metamaterials. As we can see, for any time more than 20 hours, the curing time does not have effect on the power spectral density. And these measurements were done within single gluing session. The piezo was not unglued and reglued, adding an additional factor to the experiment. Knowing this, here we can see that ungluing and regluing does have an effect, and that is presumably due to slight variations in placement of the piezo. Every time the glue cures, it hardens and puts piezo in slightly different orientation, or there might be mild differences in the location the piezo gets placed at. And as I can see, the peak features are different across both of the plots. To control this, I designed placement holders to make my placement of piezoelectrics more consistent, and the plots for these are better than the previous ones, and all the peak features are preserved across 2 plots. So the blue and the violet curve here shows taking 2 runs without changing anything and trying to compare with the variations within just taking 2 runs without changing anything to the difference I get by ungluing and regluing for the one with tabs. And I see that most features are preserved, and I could reliably analyze the acoustic properties of this metamaterial. To summarize, I also found that reproducibility of measurements was affected by using different piezos. Some of the piezoelectrics I named them arbitrarily as I, J, and K, and that was done to not assume a priori any of the physical aspects of the piezoelectric that were responsible for different power spectral density curves in the metamaterial. But it later turned out that the piezo I was more used and more worn out, and piezo J and K were fresher piezos, and they were able to produce good amplitudes of responses in metamaterials. And so I deemed that piezo J and K were fit to use for taking main primary data for the metamaterial, whereas piezo I was not. And so the solution to deal with a lack of reproducibility across different piezos was to use as much fresh piezos as possible. To summarize the experimental protocol that I've developed here, I decided to use springs with 35.2 Newton per meter stiffness. I decided to always cure the glue for more than 20 hours. I decided to also take all the measurements within single gluing session. Although the features are repeatable across different gluing sessions, they are more consistent within a single gluing session. Whenever possible, I decided to take all my measurements within a single gluing session. Also use lattices with placement tabs, and that helps me achieve reproducibility and avoid inconsistency of placement of piezoelectric every time I take a measurement. And lastly, I use as much fresh piezos as possible and allow cooling time in between measurements to reduce any thermal stress on the piezoelectric. Again, just to remind, what am I looking for in my data? I'm looking for frequency content and features like band gap. I'm looking for any other desirable phononic properties like dispersed vibrational modes or concentration of vibrational modes or plane waves in the metamaterial. And while doing that, I'm also keeping an eye out for whether there exists a parameter which I could use to tune any of the desirable phononic properties I find in these metamaterials. And any of the protocols that have been used to design these metamaterials, like uniform randomized lattice of points or points generated by Lloyd's algorithm, or the protocols that have been used to connect these points, could ultimately form a tuning parameter which we could use to control the location of band gap, let's say, or the frequency at which I see concentration of vibrations or dispersed vibrational modes or plane waves in metamaterial. And these are some of the protocols I've used, and I would later see if these do actually form a control parameter or tuning parameter for these metamaterials. First, I would like to see the. Let me just get some water. I would like to compare the power spectral density curves of metamaterials across different disorders of the metamaterials that I have. And here is an image of all the different metamaterials of different disorders and the curves I get. I find that the Bragg peak for no disorder is completely suppressed for 3 of the metamaterials of smallest perturbation 0.2 and next perturbation strengths of 0.4 and 0.6. However, I find that some of the higher perturbations, the strength of amplitudes in power spectral density curves again becomes comparable to the peak of the Bragg peak of no perturbation around some of the frequencies. And I would come back to this later after checking for dependence of these on tension. So for first of the no disorder lattice, as I already showed, the Bragg peak has dependence on tension, and that's the primary feature that I see in the curve, which does have a non-monotonic dependence on tension. For lowest disorder of 0.2, the lattice does not look very different from no disorder lattice. However, I do see that I do get a wide band gap, and it is robust under multiple tensions I have tried here. I tried 0.1 Newton, 1 Newton, and 2 Newton of tension under which each spring was held. And I find that the band gap region or any of the other features around the band gap were not changed appreciably, and band gap was not weakened by change of tension. To compare the scales of, and this is what the literature had, the computational studies have already predicted. To compare the scale at which this is happening as compared to the ordered lattice, as we can see here, the peaks in the ordered lattice are of the order of magnitude of 7 PST. However, the peak is completely suppressed once we add a small disorder of 0.2, and the band gap region exists below 1.2 PST on these curves. For higher perturbations of 0.4 and 0.6, I find that band gap region is not as strong and wide, and it is weakened by some of the features that appear in what was originally a band gap region. Like for 0.4, I see that around 5 kilohertz there are some of these peaks, and there's another peak around 8 kilohertz, whereas for perturbation strength of 0.6, I find that between 4 kilohertz and 8 kilohertz there are multiple peaks appearing which weaken the band gap region. However, the robustness under change of tension is still maintained for these curves. For higher perturbation of 0.8, I find that, and we have already seen this curve, that it does depend on tension, and different peak features in the power spectral density curve have a different kind of dependence on the tensions I've tried, and some of these features are highlighted here. Some of these features are not present across multiple different tensions, whereas others are present and do agree, whereas some others do not agree. For higher perturbation of 1, which is the maximum perturbation that have been tried on these metamaterials, the peaks seem to realign with 63 kilohertz frequency, which is the same frequency at which Bragg peak originally appeared. And while this does have dependence on tension, it's not as extreme as seen in the original unperturbed ordered lattice. So looking at the scale of these, the higher perturbation strengths could be used to change the location at which the higher amplitude peaks appear, and these peak strengths would be, the peak amplitudes would be comparable to that of unperturbed lattices, whereas some of the intermediate disorders could be used to suppress the peak features and not allow vibrations to pass through the material. And so that tells us that disorder does form a control parameter for material properties, and we could use it as a tuning parameter. Summarizing the results for disorder and tension, some of the disorders of 0.0, A equals 0.0, A equals 0.8, and A equals 1 could be used for tension measurements, sensing the tension, because they do depend on tension, and the sensitivity is very non-monotonic, so the peak features change vastly across different tensions, and that could be a potential application of these. Band gap is attained only for some of the disorders, specifically for disorder of 0.2, and the band gap is robust under change of tension. I also propose that the band gap location could be tuned, and this goes back to the original calculation of range in which I should be measuring my metamaterials, and I find that band gap region appears around the 63 kilohertz, which was the original Bragg peak, and it appears after suppression of the Bragg peak in no disordered metamaterials. And the frequency at which Bragg peak appears depends on the interpoint spacing in the original unperturbed point cloud. So by changing the interpoint spacing in the original point cloud, we could change the location at which the band gap appears. There are also other material properties on which it depends, which dictate the velocity of sound in the metamaterial, but it does remain that disorder is what caused band gap in the first place, and it is the interpoint spacing is one of the parameters we could change to change the location of the band gap that appears after perturbation of the original ordered point cloud. Also tested the sensitivity to driving orientation with respect to the lattices. Two of the orientations I tried are shown in the metamaterial picture here, and the first orientation, which is orientation A, is along one of the axes, whereas the second, which is orientation B, is at an angle to the axis of the lattice. I see that for ordered point distribution, the orientation does change the frequency response, power spectral density of the metamaterials, whereas for intermediate disordered metamaterials of 0.4, I find that there does exist isotropy in the characteristics power spectral density curve. Either of these metamaterials lack any kind of rotational symmetry. However, after perturbation, whether perturbation introduces any the probability distribution described by the perturbation cloud introduces any isotropy in the material properties would be interesting to see in later experiments. Also present some of the preliminary data for metamaterials generated from Lloyd's algorithm and Delaunay triangulation, and compare them with the primary metamaterials are used in these experiments, which involve using point cloud from uniform randomized lattices and connecting using Gabriel graph. For URL plus Gabriel graph, I did not find any diversity in the spatial distribution of vibrational modes. However, for Lloyd's algorithm and Delaunay triangulation, I did find variations across different frequencies that I measured in these metamaterials, diversity of spatial vibrational modes. As we can see that at 1 kilohertz there is concentration of vibration in the interior region of the metamaterial, whereas for some other frequencies like 4 and 6 kilohertz we do see some plane waves, and for lower frequencies there is dispersed vibrational mode. And this is similar to what has been predicted in computational studies. This study was done on hyperuniform distribution of lead in a epoxy matrix on sound on acoustic properties of that medium. So to conclude, what did I find out through these studies? I found out that disorder does form a tuning parameter. It does control acoustic properties, and around disorder of 0.2, I do actually find a band gap, and the band gap is robust under multiple different tensions that I've tried. Also propose that the location of the band gap could be tuned by changing the interpoint spacing of the original point distribution. And preliminary data also shows that some of the metamaterials generated from Lloyd's iterations and Delaunay triangulation could be used and further studied for spatial distribution of vibrational modes, and also that disordered hyperuniform metamaterials do show isotropy in their acoustic properties. And the future scope is some of the some of these metamaterials could be made using both phononic and photonic materials, which in which way we could combine the band gaps seen in photonic region and phononic region and create something called phosonic band gaps. We could also use these metamaterials for sensing tension and other physical properties. More experiments could be done on how this disorder introduces isotropy in these metamaterials and whether that is connected to the isotropy or any kind of symmetries in the probability distribution of that is described by the perturbation of points. And yeah, that is my work on these metamaterials. I will leave acknowledgements here.